afternoon, everyone. Welcome to this invited number theory session. The first speaker of this session is Professor Trevor Wooley from University of Bristol. He will talk about translation invariance, exponential sums, and Wiening's problems.
Thank you very much, and I certainly would like to thank the local organizers of this meeting. The organization has been excellent, and especially I want to thank the audience members who have stayed for this second week of the meeting and have not gone off to play Go or do other things right now. So thank you for being here. Good. Okay, so this is a talk to try to tell you about some recent developments associated with exponential sums. And I want to give you the message to take away before you see the talk, just because time tends to run away from me. So, as many people will say, and in some parts of number theory there will be criticisms in analytic number theory, it's often the case that we get pretty good estimates, but they're not best possible estimates. In fact, you're far away from best possible estimates. And until the end of 2010, really until the start of 2011, this was true of the topic of mean value estimates for exponential sums, except in the trivial linear case and in quadratic cases. In the quadratic case, there are always, even basic methods actually give you very close to best possible results. So somehow quadratic cases are special. So what you'll hear about is a new method based on an old method, which establishes either optimal estimates or very nearly optimal estimates throughout the full range for all degrees. So that's really the big news from this talk. And as you see in the bottom of the screen, in the cubic case, actually we can prove all the conjectures in full. So this is, again, the first time for degree larger than 2 that we get best possible results. So okay, before I get bogged down with just mumbling here, let's here we go. Try to introduce the topic. So I want to give you a bit of background. Why are we interested in exponential sums? Well, classically, these were referred to as trigonometric sums. And it really goes back to studying Fourier series. And these are very much of interest in analytic number theory. There are many analytic number theoretic functions which you can approximate by Fourier series. So a basic example maybe is the Riemann zeta function. I should point out that in this subject, just in case you're not familiar, we always write e of z as e to the 2 pi I z to save a bit of clutter. So if you're interested in bounding the Riemann zeta function inside the close to the critical strip, one thing you might do is apply a partial summation, and then you have these partial sums of n to the minus it. T is a real number. You should think of that as being large. And the idea is that you would try to write a Fourier series associated with this. And there's a function here which you can approximate by using a Taylor series expansion. So in general, you have some function f, capital F, which is reasonably smooth. And you can write down some polynomial expansion to f. And your function which you're trying to estimate can then be estimated in terms of an exponential sum of some degree k. In the case of the Riemann zeta function, if you're close to the 1 line, then this degree k may actually grow with x even, so it may be really rather large. If you're close to the half line, then relevant k's might be closer to a half, closer to 2. So you know, this situation that you're interested in really depends on the specific function, but it's certainly the case that these exponential sums over polynomial arguments are a basic object to consider. And this all goes back to work of Hermann Weyl almost a century ago. So Weyl was interested in these exponential sums for purposes of equidistribution results. And so they're also called Weyl sums as well as trigonometric sums. And I just want to sort of indicate briefly what goes on in Weyl's method. sure many people here are not really into this area. So Weyl's method is one of the most natural approaches to bounding these exponential sums. I already told you that linear exponential sums, degree 1, that's sort of a trivial situation. And the reason it's trivial is because if this argument of the exponential sum is linear, because e of z is e to the 2 pi I z, this is basically a geometric progression, and you can believe that there are effective ways to estimate what goes on with the geometric progression. That's something which is easy to analyze. You know how to sum a geometric progression. When you have higher degrees, a natural approach is to try to reduce the degree by some simplifying argument. And actually, already in Ben Green's talk this morning, this was underlying some of the work. So here's a little argument. If you square the exponential sum, the absolute value of it, you get the exponential sum times its conjugate. And you can rewrite this, really there are two independent variables here, but I can rewrite what's going on in terms of a shift of absolute value at most, the length of the exponential sum, and then a sum over a set of variables which are sitting inside some subinterval of 1 up to x. And you get this difference of the values of this polynomial, sort of a difference operator. It's almost like differentiating the polynomial. And so if I write down what this difference is between the two values of this polynomial, it factorizes with an obvious factor of h and some lower degree polynomial here. So if c had degree k, then this polynomial here has degree k minus 1, so it's simpler. If I started with a polynomial of degree 2, then down here I'd have a linear polynomial in x, and you can imagine that I can estimate that, and then get back an estimate for the original exponential sum. Okay, so if you iterate this kind of approach using Cauchy's inequality, that was really underlying some of what Ben Green was talking about this morning, then you get an estimate which is inflated by some power of x. So I perform sort of k minus 1 operations of this type. So I'm looking at a 2 to the k minus 1 power of this exponential sum, and that's bounded in terms of something which is just linear in x. So I can sum that, and this way you get some estimate. I mean, if you get to grips with all of the details, then what I have at the bottom of the screen here is the kind of estimate that you can extract from this kind of argument. So let me just summarize that at the top again. What's the quality of this estimate? It's worth asking yourself that. Well, you can always apply Dirichlet's approximation theorem to provide an estimate for the lead coefficient of your exponential sum. So you've got a rational approximation, a over q with n q co-prime, and alpha k minus a over q is at most 1 over q squared. And if you choose parameters appropriately, if your alpha k is not too well approximated by rationals, you can sort of assume that q lies between x and x to the k minus 1, say. And if you're in some subjects, like ergodic theory, you might call this Diophantine condition on alpha. This is sort of a natural condition to impose. Almost all alpha satisfy this condition. Then the strength of this estimate is better than the trivial estimate, which is x by a power x to the 2 to the 1 minus k. So something which is exponentially small. The exponent here is exponentially small in terms of k, but it's definitely non-trivial. Excellent. So this is a pretty robust method for deriving estimates for these exponential sums when the lead coefficient is not well approximated by rationals with small denominator. The improvement over the trivial estimate is small, as I just mentioned, but positive. And one other feature, if you're interested in applications, for example, in theoretical computer science, this method is not good if the characteristic that you're working with is small. So here I'm talking about the integers. You might be interested in what happens if you're looking at polynomial rings with coefficients from a finite field fq, for example. But if the characteristic is small, this method doesn't give you any sensible estimates. So that's another problem with this method. So that's a very classical method. I want to tell you about a method which improves on this. And here we go. So that's Vinogradov's approach, which is also old, about 80 years old. So what goes on in Vinogradov's method was a bit more complicated to explain. So in the previous method, you have a very natural approach. You try to reduce the degree of a polynomial argument. If you reduce the degree enough, you get to a situation that you can understand. Vinogradov's approach is to consider the average of this exponential sum as you integrate over all values of alpha. So all of these arguments alpha. So if you integrate over all of these, you're not getting an estimate for the exponential sum, but you're learning about what's happening on average. And Vinogradov's idea was to use this average information to say something about what happens for a fixed k-tuple alpha. And I can quickly explain that. So first of all, I want to just explore what we should expect for this mean value, which is typically called JSK of x, so it's the average, it's the 2s moment of this exponential sum of degree k. And the key observation for this subject is that by orthogonality you can relate these mean values to the number of solutions of a system of Diophantine equations. So if I integrate over the k-dimensional unit cube, multiply all of this together, what you get is a sum over 2s tuples of integers between 1 and x of all these linear combinations of powers of the x's and y's here. And the only time that you get a non-zero contribution by orthogonality is when all of these polynomials vanish simultaneously. So here we are, we've got a system of Diophantine equations of degree 1 up to k in 2s variables, and we're counting all of the solutions between 1 and x. So that's what this mean value counts. So that already gives one lower bound for the number of solutions. If we want to understand how this Vinogradov approach works, we should think about what we should expect, what we should conjecture for the size of this mean value. So that's what I want to do next. So one lower bound comes from those diagonal solutions. I'll come back to that in a moment. Another lower bound comes from what is essentially the density of solutions. And to get at this, let me just make a rather simple observation. So if I look at values of the coefficients which are extremely small, so alpha j was the coefficient of the x to the j term. If I assume that alpha sub j in absolute value is at most capital X to the minus j divided by 100k, say, for each j, it's very small. But if you think about it, the value of the argument of the exponential sum in that situation is also small. It's at most 1 over 100, let's say. So that means that when I add together the exponential of this, e of this polynomial, I'm basically adding together something which is very close to 1 for all of the summands. So this expression is larger than a constant times x. It's very nearly capital X in size, in fact. So it's that's a very simple lower bound, which is applicable, well, almost nowhere, but certainly when you're very close to the origin. But already that gives you a reasonable lower bound on the size of this exponential sum for these moments. So if we have 2s copies of this exponential sum, and we stick to this neighborhood of the origin, then we're getting a contribution just from that neighborhood, which is nearly x to the 2s, well, times the measure of the set we're integrating over. And the measure of that set is of order x to the minus a half kk plus 1. That exponent comes from summing up the degrees between 1 and k. So that lower bound is also majorized. It's bounded above by the integral over the whole of the unit cube, which is just jsk of x. So that gives me one lower bound for this mean value. It's a trivial lower bound, but it's actually corresponds to the density of solutions. Another lower bound, which is even simpler, uses the observation we made on the previous slide. So by orthogonality, the mean value corresponds to the number of solutions of the system of diagonal equations. And if I just set xi equal to yi for every I, there are capital X choices for these variables, and the total number of choices for all of those diagonal solutions is like x to the s. Got s copies of those diagonal solutions. So if I add these together, I get a lower bound for the mean value. And that lower bound is actually the expected size for this mean value. We really do conjecture that this lower bound corresponds to the true state of affairs. If you dig into the analysis a little bit, you can see that there are extra reasons for believing that. It was a simple argument I gave you, but it's even a reasonable idea. So, as usual in this kind of subject, we'll add in an extra x to the epsilon for safety. So for each epsilon greater than 0, no matter how small, we expect that this mean value is bounded above by x to the s plus x to the 2s minus a half k plus 1 times x to the epsilon. Good. Okay, so now we know what to believe. Here's the classical version of Vinogradov's mean value theorem, which has been developed over many years. So work which gives estimates of this basic type has been ongoing since the time of Vinogradov and into the 1990s even. So you can see here that the upper bound that's available has the same shape as the upper bound which we expect to believe, which we believe, yes. Not only do we expect to believe it, we even believe it, but we don't know it to be the case. And we miss this by a positive number eta, and that eta depends on s and k. So remember, this is a 2s moment of an exponential sum of length capital X of degree k. And that eta decays exponentially with s. So you can see that when s grows like k squared, maybe times log k, but this term is really pretty small. So we get very close to this estimate. And if you choose a suitably large constant multiple of k squared log k, you can even sort of bootstrap your way to proving the upper bound here. So the classical situation is that you can prove this main conjecture when the number of variables, the moment, is growing like, well, actually this moment is an even moment. You've got twice as many variables as 3k squared log k. So this sort of conforms to the first line of my message from this talk. This is a pretty good estimate. K squared log k, sorry, let me go back. K squared log k is not a bad limit on the number of variables you need to establish this estimate, but it's not really very close to the optimal estimate. We'd expect to achieve an estimate which is optimal already if you have a half k plus 1 variables. So we're missing by log k, which when k is large is a big miss. Excellent. Okay, so what next? So I promised that I'd try to tell you how to estimate exponential sums without using Val differencing. So here's a brief sketch of that just to try to convince you that I wasn't talking garbage. Okay, so what we know about estimates for mean values of this exponential sum, and what we'd like is to estimate the exponential sum for a fixed value of alpha 1 up to alpha k, these coefficients. And one observation is that if you choose some other k-tuple of coefficients, let's call them beta 1 up to beta k, and the betas are all very close to the alphas, then the exponential sum doesn't change much in size. And this is basically the same argument as I gave when I was giving the lower bound. So the derivative, if you think about sort of some kind of Taylor expansion or mean value estimate, the Taylor series, the derivatives don't increase very rapidly. So if you change the argument not very much at all, then the exponential sum just doesn't have room to change appreciably. So if you stay in a very small neighborhood of the k-tuple of coefficients which you're interested in, then the exponential sum really doesn't change much in size. Okay, so that's one observation. Second observation is that we have a sum from 1 up to capital X in the original exponential sum. So if I shift all the variables by some number little h, which might be 1 or 2 or something small, and I shift the range of variables backwards by the same amount, then I've just written down the same thing in a more complicated way. So I did nothing to the exponential sum at all. That's very boring. However, I can expand all these powers by the binomial theorem and collect together terms, and I get a new exponential sum, or a new argument, polynomial argument of degree k, with different coefficients, and I'll call these alpha superscript h here. So you can imagine, I mean, alpha 1x, alpha 1 is still the coefficient of x, but the coefficient of, sorry, I shouldn't say that. So alpha k x to the k still occurs. The coefficient of x to the k minus 1 contains an extra term involving k times h times alpha k, as well as the original coefficient alpha k minus 1, and so on. So I get some sort of change in the coefficient, but also the length, the summation range changed. But you see, if the h is small, I can add in and subtract off the tails of this summation, and it doesn't change the sum by much at all. So if h here is rather smaller than x, then I get what presumably is a new k-tuple of coefficients, and the size of the exponential sum really doesn't change very much. So if you apply this idea and pursue it through to completion, the idea would be that you can collect together a whole bunch of neighborhoods, these small neighborhoods of the original k-tuple of coefficients, alpha. If I add together the contributions of all of these neighborhoods, if they're disjoint enough, let's say I have capital N disjoint neighborhoods, then if I add together all of their contributions, that's bounded above by the integral over the whole of the k-dimensional unit cube, and that's the mean value we're interested in. So indirectly, what I have is an upper bound for the exponential sum I'm interested in terms of the mean value, if I sort of unravel all of this. That's as long as I know that these neighborhoods are sufficiently disjoint. And so if you work out the details, then you find that you get an estimate very similar to the Weil estimate, involving the mean value of this Vinogradov's mean value theorem, the 2s moments of the exponential sum, actually of degree k minus 1, not even k. And, well, maybe I'll interpret that. So if you look at the situation we looked at before involving Weil's inequality, there we had a poorly approximable lead coefficient, and we get an estimate for the exponential sum which saves a power of x, which is exponentially small in terms of k. Well, with this new method, using the classical version of Vinogradov's mean value theorem, you get a similar estimate, but now instead of something exponentially small in terms of k, you get something which is like 1 over k squared log k, 1 over 4 times k squared log k. So that's much, much better. And as before, it's a pretty good estimate, but it's far from optimal. And so, for example, this sort of thing goes into the best zero-free region for the Riemann zeta function that we have available right now, $1 million problem. So what I'm interested in is improving this mean value estimate because it has applications. Firstly to Weil estimates, but also many other applications as well, and I'll say something about all of that. So let me just summarize what classical estimates are available from the body of work on Vinogradov's mean value theorem up until about 2010. And here's a reminder of what we conjecture to be the case. So the conjecture was known to be true, even in a very precise form, in the quadratic case. The linear case is trivial. And then it was also known to be the case, you get this diagonal behavior if s is k plus 1. For s smaller than k plus 1, actually, this is all trivial. It's sort of Newton's formulae on roots of polynomials. So there's really just one case extra where we have this diagonal behavior. And there are very precise versions of that result. And then for larger values of s, there are explicit values which actually come from an argument of Hoare involving Weil differencing in a different way. And then for large values of k, instead of needing 3k squared log k, the most precise versions available from the 90s need just k squared log k. You still miss the conjectured result by something of size log k, something going to infinity as k goes to infinity. Okay, so now I get to the point where I can tell you about developments. I should tell you about them reasonably rapidly, I suppose. So the big news is that this main conjecture, all these conjectured estimates, is very nearly known to be the case now. Very nearly. So So just to remind you, for k equals 1 and 2, the classical situation was we use these results, and now we can prove this with this conjecture in full for the cubic case. So it's the first time for any exponential sum that we have a mean value estimate, even if you put restrictions on the sum, where you get the conjectured estimate, the density result, the full conjecture in a degree larger than 2. So this is something different. So also, and maybe in many ways this is the most significant development, we now have this diagonal estimate. That's the first part of the main conjecture, not for s going all the way up to a half kk plus 1, but going up to a half kk plus 1 minus about 1/3 of k. So that's not the whole thing, but it's really pretty close. And it's certainly way better than k plus 1. K plus 1 was not so impressive. Now we're very nearly the whole of the way. And when k is large, well, you can work out explicitly what happens, of course, but all that you need is for s is at least as big as k times k minus 1. So before, classically, k squared log k, and now just k times k minus 1. Okay, well that's not a half k plus 1, but it's only a factor 2 away from that. Okay, so altogether that's really rather close to the conjectured estimates, and I can say a little more in that direction. So you can push these methods further, and if you want to get an estimate which is valid for all values of s, then something which summarizes, well, which is a convenient way to approximate what we know, is that you miss by, at worst, 1/3 of k times, x to the 1/3 of k. And if you think about it, you know, s typically maybe you can think of as being of size k squared, so this is really rather small deviation from the conjectured estimate. And another observation which maybe should convince you that we're very nearly, very nearly proved the whole of this conjecture, is that if you happen to know the main conjecture, if you happen to know the main conjecture for the specific value s equal to a half kk plus 1, then it's easy to show that the main conjecture holds for all values s. So in some sense we're just 1/3 k variables away from doing this out of order k squared variables. So any way you look at this, this is very close now to the whole of the main conjecture. Okay, well you may say that, that proving this conjecture is sort of a technical game and who really cares, but remember there are lots of applications for these things, so let's talk quickly about some applications. So one application, which is one of my favorites, is to Waring's problem. So here we're interested in representing positive integers n as sums of s k powers, and this is a generalization, if you like, of Lagrange's 4 squares theorem. He showed that all positive integers are sums of 4 squares of integers. So a basic Diophantine problem. And, well, let me just tell you what to expect. So if you apply the circle method and make every conjecture that you want to make, then you would expect that with k plus 1 or more variables, there should be an asymptotic formula for the number of representations, which involves some quotient of classical gamma functions. And then there's this other object, which is a bit harder to understand, the singular series, which actually is a product of p-adic densities, so it's very well understood, and a growth rate which is like n to the s over k minus 1. So this number of representations under reasonable conditions, some congruence conditions in particular on n, this number of representations is expected to go to infinity roughly like n to the s over k minus 1, as soon as s is at least k plus 1. Great. Okay, so a bit of notation so that we can understand when we've proved something interesting. So I call G tilde of k, tilde looks like an asymptotic formula symbol, so G tilde of k is going to be the least number t, with property that whenever you have more variables, or at least as many variables as t, then this asymptotic formula, which we expect to be true, is actually true. So it's just a way to summarize, to avoid me writing down lots of words and formulae. Okay, so how is this connected with Vinogradov's mean value theorem? Well, there's an easy way to connect the basic exponential sum in the subject, which is the sum of e of alpha x to the k to the exponential sum which we were studying before. And maybe, because time is marching along, I'll just summarize this by saying that by orthogonality, if you sum over all the possible values of sort of lower degree polynomials that occur when you are examining mean values of this exponential sum over the full polynomial, this gets you back to the exponential mean values of the exponential sum just over k powers. And so then there's an easy relation with the mean value we were just studying. Okay, so we want to, I should say, what historically is the case, so you can see what the new developments are. And, well, I mentioned vowel differencing, so if you apply vowel differencing, this is what Hardy and Littlewood did in their seminal work in the 1920s, and Hua perfected this method. So you get an upper bound for the number of variables you require to prove the asymptotic formula, which is exponential in k, something like 2 to the k. And by the end of the 1990s, well, there were a number of results you can see here. So basically, for small values of k, the bounds were a little better than Hua's bound, just very slightly better. And then you could do sort of a hybrid version of vowel differencing and Vinogrado's mean value theorem for smaller values of k. And then for large values of k, the number of variables that you needed, instead of being like 2 to the k, is a constant k squared log k times, well, numbers which were slowly whittled down over many years. Okay, so what can we say now? So, if you remember, the mean value estimate which we got for jsk of x was optimal already when we had k times k minus 1 variables. So if s is at least as big as k times k minus 1, then we get an optimal estimate for this new mean value which we're studying here. And automatically, just for free, that gives an upper bound for g tilde of k, which is like 2k squared minus 2k plus 1, for all k greater than or equal to 3. And that already improves on the previous state of knowledge for k as small as 6 or 7, thereabouts. But you can refine all this. And this is still ongoing. There's still refinements which are coming out of these methods. So it's fair to say now that the vowel differencing methods have been superseded already when k is 4 or more. So the only situations where vowel differencing is useful for this kind of problem are k equals 2, which we already knew what was going on, and k equals 3. For large values of k, instead of getting this result, which was like k squared log k, you get, well, we could already see you get 2k squared as an upper bound, but even you can get something which is basically 1.5 times k squared. Pretty small. Okay, so I should say a little bit also about estimates of vowel type. So recall we had vowels inequality. You get an estimate for your exponential sum, which is small if you don't have rational approximations to the lead coefficient, which are too good. Denominators are too small. So before I can summarize what this pointwise bound estimate that we derived before was. So this gives an upper bound which gives you a new exponent depending on the quality of your mean value estimate for jsk minus 1. And I can extract from that a bound which replaces the exponent 2 to the 1 minus k by something which is like 1 over a constant k squared log k. And now with the new work, a constant k squared log k is replaced by, well, 2 times k minus 1, k minus 2 for k, at least 3. And so this supersedes vowels inequality even for quite small values of k. And there are various applications of this kind of thing. As you can expect, this was a basic input to many estimates in analytic number theory. Here's a result for uniform distribution mod 1. So this double modulus is the distance to the nearest integer, a basic uniform distribution result. Okay, so these exponents are better than what one would achieve before by an amount which goes to infinity as k goes to infinity. So anyway, there are many applications. This is just a summary of some results which use Vinogrado's mean value theorem and can be improved from recent and past years. There's even some interesting work on the sum product theorem, which has come up recently. solutions of congruences and short intervals, and so on. Anyway, lots of results. This last one, geometry of spaces of morphisms, comes from looking at the corresponding function field analog of Vinogradov's mean value theorem. So there's lots and lots of work, and this is just a subset. So this can all be improved. In some cases, actually, you get results which give non-trivial results now, which were just not non-trivial previously. Time is running away from me. Okay, so I'm going to try to give rapidly a sketch of the underlying ideas. And I'm not expecting you to follow what happens here. So there are 2 points I want to make. And I'll isolate those 2 points. And I hope that you'll just trust me in what I say as I run through this. I'm sort of going to run through it in order to try to convince you that what I say might be correct rather than to have you really follow what's going on. So the basic setup when you're estimating this mean value is that you want to measure how close you are to the conjectured estimate. So for large values s, the conjectured estimate is like x to the 2s minus a half kk plus 1. And there's a way to measure how close you are to this involving some infimum of permissible exponents. And the idea is that there are large values x where you get a lower bound which is pretty close to this, and of course for all large enough values of x, the upper bound is also pretty close to this. So that's sort of a way to calibrate where we are in this kind of game. What else? Well, this is an important point. This is something I want to emphasize. So translation invariance. So the important feature of Vinogradov's mean value theorem, the system of equations, is that it is translation invariant. What do I mean by that? Well, if I have a solution of a system of equations, which we've been talking about, if I shift all of the variables by an amount a, then this is still a solution of a system of equations. And you can see that just by using the binomial theorem. If I expand all of these terms, I get a linear combination of polynomials from the original system, all of which are 0. So it's still 0. And I can go backwards, obviously. Shift one direction, shift the other direction, it's the same story. Okay, so shift invariance is fundamental. And now I'm going to be relatively rapid fire and draw your attention in a moment to an important feature. So the basic setup is you want to choose an auxiliary prime. It's a small power of x. You might think of it as being something like x to the 1 over k for now. And you break up your variables into arithmetic progressions modulo powers of this prime. So initially, what we're going to do is break up the the exponential sum into arithmetic progressions mod p. And I can use Holder's inequality to bound the 2s power of the original exponential sum in terms of what goes on in an arithmetic progression mod p. And rather than estimating a 2s moment, I'll estimate a 2s plus 2k moment. So I perform this operation with 2s variables and leave some alone. Okay, not to worry about that. This is just leading up to the next important feature, remember. So by orthogonality, this mean value counts the number of solutions of a system of Diophantine equations, and some of these variables are in an arithmetic progression mod p. And if I use the translation invariance, this is where I'm using translation invariance, and I can shift everything by this number c, so that I see that every solution of this equation corresponds to a solution of a new system of equations where the powers sort of come out of the equations. So instead of having these arithmetic progressions, I now get pure powers coming out. And that means that in the original system of equations, there's a congruence condition on the variables. So this is the second important point. That translation invariance leads to, well, we set things up so that we artificially created a congruence condition mod p. Now we've created congruence conditions, we've created congruence conditions modulo powers of p, all the way from p to the 1 up to p to the k. Those are much stronger congruence conditions. So we won something in that process. And you can apply Hensel's lemma in a form to actually sort of lift these solutions from solutions mod p to solutions mod p to the k. So just take away from this slide that there's a way relatively efficiently to extract from this congruence condition a constraint that the variables pairwise are congruent to one another modulo p to the k. Good. and being very rapid. Right, so we have this congruence condition, and that's a constraint which, if you take theta to be relatively large, like 1 over k, forces a diagonal condition. And by translation invariance, what's left after you force the x's and y's to be equal, what's left is that you get a system of equations again of the same type, but with variables in a shorter range. So in this way, you get an upper bound for the number of solutions, which is relatively strong. This is the classical version of the method. And you can exploit this, you get an upper bound, which is the classical bound. Great. And so, just very rapidly, what goes on in the new method, a hint of what goes on, is that you try to apply this constraint which we generated at some expense, constraint modulo p to the k, in a similar process to get a new constraint modulo p to the k squared. And the argument, well, in the interest of time, I think I'll fast forward through this. The estimate that you get ultimately depends on a mean value which has very similar shape to the one we just considered, but where the variables are now constrained not modulo p, but modulo p to the k. So here we are. That's the point that I want to make. So efficiently, we're able to get an estimate for the number of solutions of the system of equations where instead of working mod p, we now get a constraint mod p to the k. And this forces a constraint by similar congruence argument on the new system of equations, not mod p to the j, but p to the jk, and ultimately a constraint modulo p to the k squared. So it's a much more efficient approach from before, and you can iterate this process. And that's a hint at what goes on there. I think I may have 2 minutes to give just a hint about what happens in greater generality. So let me just say that you can apply translation invariance to more general translation invariance systems, and the same kind of approach applies. And this gives really general estimates for any exponential sum over a polynomial. You just create a translation invariance system. Here's an example. And you get an upper bound which is very simple to explain, to describe at least. It depends on the number of equations that you have in your translation invariance system. Here's an example. The total degree, the maximal total degree of the system, and the sum of all of the degrees in the system. And as long as the number of variables and the mean value is larger than the number of equations times the total degree plus 1, you get your optimal estimate again. Just the same as in Vinogrado's mean value theorem. It's very general. And one last comment. So translation invariance is important, but you have approximately translation invariance systems. You don't really need translation invariance at all. You can apply similar sort of ideas to deal with, well, powers which are not the full set of powers. And actually you can replace these by well-approximated functions of variables, so relatively smooth functions also you can get estimates. And the same sort of methods work. This actually already improves some very recent work of Bourgain and Ciprian-Demida. Okay, so my main message from this talk is that if you're in a world where you're using Weyl differencing, then you should think about efficient congruencing, because it's almost surely better, even for small degree. And I hope that maybe you're convinced that in many situations you get extremely close to the conjectured estimates, which is really very unusual in this kind of subject. So we already have optimal estimates for cubic case and very nearly in complete generality. And that's the end of my talk. Thank you.
Are there any questions or comments?
Yes. What sort of improvement do you get for the zero-free region?
Oh, yeah. So the question was, what kind of improvement do you get for the zero-free region? That's a really bad question, Harold. So, of course, it's an excellent question. That's one of the things that I wanted to try first of all, of course. Unfortunately, the asymptotic nature of the zero-free region, which involves 1 over a power of log. If you're not an expert, this doesn't mean anything. You get slightly inside the critical strip. So asymptotically, as you move a long way up the critical strip, the rate of growth of this zero-free region doesn't really change. But the constant does. The constant does. And so it looks as if that leads to a reasonable improvement of the constant, but not a mind-blowing one.
Yes, but that might be crucial, because that type of zero-free region is completely useless in practice, or has been so far. It's worse in the classical quantum practice, and because of this, it might not only be.
Yes, that's an excellent project for somebody who has a lot of time on their hands.
Okay, any other questions? The local organizing committee prepared a gift for the speakers.